Hello, this is Questionable Coding with Vladimir, and today we're going to talk about a data structure called tree. It's a very broad topic, so I'll try to be brief and select only a small subset of knowledge that we need to obtain. And it will be a good foundation to start from to discover different types of trees and where we can use them. So at first we'll start with a general description of trees, then we'll go through binary trees and binary search tree, because it's the most famous type of tree and probably you face it during some interview or maybe in your coding practice. We'll cover traversal of those trees and common methods that are usually implemented for such type of trees and some optional methods. We'll go through complexity of those methods and main operations, and we'll also implement those insertion and traversal of binary search tree. So it's quite a plan, and let's start right away. So let's first talk about trees in general. It's a hierarchical linked data structure, which means there are different nodes which are linked together, similar to a linked list. And it can also be described as a special case of a graph, which should be acyclic and directed, but I think it will complicate things a bit. So what's a node? Node is like a container for some data. It can be just integer data like number 50, and also some links to other nodes. It can be 0 nodes or like 100 nodes, as much as you like. On the picture you see a red root. There can be 0 or 1 root. If there are 0 roots, then the tree is empty. And there can be more than 1 root. All the tree goes from 1 root. There can be 0 or more subtrees of the root. So there can be only 1 node or a huge tree. Or something in between, of course. Each node has 1 parent and 0 or more childs. So on the picture, you see that there are nodes that are in blue, and they are called leaves. They don't have children at all. And there are internal nodes which are in green. By the way, root is also internal. And those nodes, they have children. What about binary trees? We apply all the rules that we discussed before, and we introduce a new rule that each node points from 1 to 2 child nodes. So it's not an unlimited number of children, as we discussed before, but it's limited to only 2. You can have 1 node, you can have 0 nodes, or the maximum number is 2 once again. We have also a binary search tree, which is like evolution of what we saw before. So we apply all the binary tree rules, and we add a new rule there, or maybe 2. We can divide it into 2 rules as I did here. So the new rule is that the node key is bigger or equal than all keys in its left subtree. And another rule is that this node is less or equal than all keys in its right subtree. So we see we have number 50. We know that on the left subtree all the nodes will be less than 50. And this rule also applies to each node recursively. So for example, if we take a node with key 41, we are sure that all the nodes to the left, it's only one node, 33, will be less than this node. Why do we need this? It helps us a lot when we want to find something or insert something. Because every time, if the tree is balanced, so it has like a good number of nodes to the left and to the right, we'll discuss it a bit later, then each time we just divide our number of options into 2. Same we have with binary search. That's why it's called binary search tree. And each time we just reduce the number, and we get a very good complexity, a very small number of steps to find something or to insert something. But there can be an unbalanced tree like this. For example, we use 50 as our root node, then it will insert 99. According to the rule, we need to insert it to the right. And then we insert something even bigger, and something even bigger than everything before. and with our rule we just add it to the right, to the right, to the right, which creates just like a linear list, and it lacks all the benefits of the tree. So if we want to add something even bigger, then we need to go like 4 times here, and it's the total number of nodes. So we better watch out, balance tree if we need it, or have such data that is not that bad. So if it's an ordered list, we won't create a good tree from that. Now let's talk about the traversal. So traversal is going through elements of the trees, and there are different ways to do that. First one is pre-order. We won't concentrate on that. I think we better go to in order option and cover it in details. So when we do it in order, we first visit left node, then root, then right. And it will give us a list of numbers from the smallest to the biggest one, which is kind of cool. So we just have a sorted array here. So imagine we'll try to do it like one by one. Imagine we start with root. We don't output root right away. At first we need to follow the left node. So we go to 30 and we apply the same rule. We say that, okay, we first go to the left, and there is also a left node. So we go here, and it's a node with the key 4. And we try to go to the left here, but there is no node here. So we are passing this step and go into the next step, which is called root. So the root is 4, and we output it. So the first number is 4, as you may see. Then we try to go to the right, but there is no right node here, and we're done with this node. So we are returning back to 30, which already had left operation done. Then we need to output the root. So we output 30, and then we go to the right. When we go to the right, it's 41. We apply in order rules once again. So we first need to go to the left, and we go to 33. And we try to go to the left, and there is null. Then we output the root, it's 33. And then we try to go to the right, which is also null. And this is how we return to 41. And 41 has root and right operation left, so we first execute root, have 41, and then we try to execute right, but there is no node to the right. I think you got the idea. So after that, we return back to 30, which is also already done. We already checked the right part, and we return back to 50. And we left 50 when we just did left for 50. So we do root for 50, and we output 50. So we're in the middle of our tree, basically. And then we go to the right, and we'll continue that logic. So I recommend you to do it yourself. It's quite easy. So if we compare it to pre-order, it's a bit different. So at first, for pre-order, we output root, and we see it that the first node to output is 50. Then we go to the left and reapply everything, all the rule. We output 30, and so on. So this is a recursive approach that you just need to go through once and you understand it. Another traversal is post-order. When we first go to the left, then we go to the right, and then we go to the root. In that case, our root node will be the last one. And also we have a different thing. It really differs comparing to other traversals. It's level order, or breadth first search. Even though we're not searching for anything, we just go in through the tree, traversing it. So what we do here, imagine that 50 is the first level, 30 and 99 is the second level, 4, 41, 33, 160 is the third level, and 33 is the fourth level. So it's like layers of our tree. And we go one by one, outputting those numbers. What about common operations? Standard operations, it's insertion, deletion, and contains. It's like search. We also covered traversals, so pre-order, in-order, post-order, and we have optional operations like find common ancestors between two nodes. You can find this during interviews. Get diameter, it's maximum distance from one node to another through root. It's also an interesting task to tackle. Size, max, mean of the tree, and breadth first search. I also included it in optional traversal. Okay, so what's the complexity of binary search tree? If it's balanced, then it's big O of log n, because we're doing the same thing as in binary search for array, sorted array. Deletion, it's also the same complexity, and search also the same. So it's very efficient data structure. And now let's go to the implementation of insertion and traversal. Now I want to show you the traversal of a tree, and for that I'm going to LeetCode because they already have tests and a task for in-order traversal, and it's always easy to reuse their tests. So what we have here, we have a tree node which consists of value, left node and right node, which can be null. And we need to return an array of numbers, and we're giving the root to start from. So when you understand the recursion, it's quite easy to traverse a tree. But if you don't, you spend some time doing that. So let's start with checking if root is null. If let's say root equals null, then we will just return an empty array. Now let's create the result array. I think we can use const because we will be just adding to this array. And what we're going to do next, we're going to check if root has a left child, in this case we'll go further, and we're going to launch the same function, but passing this left node. So we're gonna go deeper. But we don't want to just go there, but we want to apply this, the result of that call to our results. So we're gonna push. And we'll expect an array from this inner call. That's why we need to spread it. And push supports multiple arguments, so it will be that easy. Okay, that's one thing. Then I'll jump to the end and I'll do the same for the right node. Okay, and in the middle we need to push the result of the current node itself. For that we need the result and push the root value. Okay, and here we need to return this result. And let's hope for the best. We'll just run the code. It's finished. I'll click submit to run all the tests because there are more tests. Yeah, and it accepted. So that's pretty cool. So what we have here is, first we check if it's an edge, not the edge case, but it's a case when our recursion will go back. So if root is null, and this can be any node that we passed there, so it's not only root, but we treat it as the root. We can call it like a current node if it's easier for you, but yeah, let's leave it as root. Then we just return nothing, and then we have a result, and we'll aggregate all the information in the result. So at first we check if there's something to the left, and we go to the left if it's there, if there is a node. And then we push, after we've done the left part, we push the root value, and then we do the same to the right. So as you remember, our in-order traversal requires left, then push, then right. But what if you want some other type of traversal? For example, you want to first post-order traversal, for example, when the root must be in the end. Then you just change the order of the lines. That's simple. Same with pre-order. You can also only change the order of the lines. So this is a nice trick. Okay, let's finish with the traversal and try insertion. Now we're going to understand and code how to insert a node into a binary search tree. First of all, what is a node? It's a class which has a constructor. We pass data to the constructor, and we have this left and right child equal to null, and data equals to data. And we're going to use this node in binary search tree, which has a constructor, and it's very simple. It just sets null to the root, so it's empty by default. And we have an insert function where we'll also pass data and use it. So how we're gonna insert and just visualize all the process? So on LeetCode, I'm using a tool called custom test case, and we can pass an array and it will draw a tree for us. I hope you can see the numbers. So 20 on the top, 10 to the left, and 66 to the right. It's a proper binary tree because all the nodes to the left are less than the root, all the nodes to the right are more than the root. And what if we want to insert, for example, 15 here? So at first we'll compare it with the root, and if it's less than 20, and it is, then we go to another node. It's 10. We go to the left, so we compare it to 10, and 15 is bigger than 10. Then we're going to go to the right, and there is no right node. Then we're going to create it, so it will be 15 here. Okay, that sounds easy. Let's try to code it. So what we're going to do here is first we need to create a node itself. So it will be const node equals new node data. Then we'll check if the root is still empty, if it's like a default empty tree. Then we're gonna assign, gonna create a new root. So this root will equal node, and that easy. So we just return from here. This insertion is done, but it's a private case. It will be harder afterwards, and then we need to keep the current node. So let's create a node called current. And first it will be equal to this root. Then we are going into an infinite loop that will just break manually. And what we do here is we compare our data to the current node value. If data is bigger than, let's say, if it's smaller first, I think it will be more in order. If data less than current data, then we'll go to the left, and otherwise we'll go to the right. So we'll check if there is current left. If it's equals null, then we'll create just a new current left, and it will be equal node. And we can return from here. Same as we did for root. I think it's very similar. And I think I'll just copy that. So current right, if we went to the right, we first check if current right is null. And if it's null, then we assign a node. But if it's not, then we update a current node. It will be current left, so we're going deeper to the left, and the cycle restarts again. Same here. If there is something to the right, then we will go deeper to the right. And that's it. So while we'll be going until we'll find a situation when there is no left or right node, depending of our comparison data with the current data. And that should be working. So what we're going to do next is we're going to run the script. I have a small prepared insertion. So we create a tree, then we console log an empty tree just to make sure. Then we insert 50, 31, 60, 35, 51, 99. And then this code, I think you shouldn't follow it too much. You can look through it, of course, but it will create a string that we can reuse on LeetCode. So it will traverse the tree and create a proper string that we can use for visualization tool in LeetCode. Sorry. So let's run it. So this is an empty tree and it looks good. And here we have all the nodes with its children. Most of them will be null. So let's check it on LeetCode. Yeah, if it's a property tree, let's look at it. So it's 50, then we added probably 31, then we added 35, 60, 51, 99. So we can see that everything to the right of each node is bigger than the node key, and everything to the left of each node is smaller than the root key. Yeah, that's how it's done. So it's a working insertion. So today we covered insertion and traversal of binary search trees, and it's just the beginning of a broad topic of a journey into trees and graphs. So I recommend you to spend time on that because you'll face it during interviews. There will be a lot of specific tasks about trees, especially about binary search trees. So it will be useful just to know them well. And I hope you like it. I hope it was useful. Stay tuned. We'll have more videos on different data structures, and not only.